Okay, derive relations via implicit differentiation. Now what we're going to do implicit differentiation after. We're going to do this the normal deriving way first, just so we appreciate the difference and why this is actually so handy. Okay, so we're going to start with a relation. X squared plus y squared equals 1. No points for guessing. Unit circle. Set it on 0. Brilliant. Okay, so I want to find the gradient when x is equal to these particular values. Fine. Well, to find the gradient of this thing the old way, we're going to need to reorganise. And hopefully we're happy that we get plus or minus root 1 minus x squared when you fiddle around with it for a bit. Brilliant. Okay, well, from there we want to derive. So y prime. What do we get? Okay, derivative, I'm going to keep the plus minus. Derivative of the inside gives me negative 2x. Derivative of the outside gives me a half. And we're going to get over root 1 minus x squared. Cool. Neaten this up, 2 and the half cancel. I'm going to write this as minus plus, just meaning it's the other way around. Those cancel, we get x over root 1 minus x squared. Okay, we had to do a little bit of work. Wasn't the worst thing in the world. Brilliant. Okay, so we can sub these in now. 0 into this, 0 over 1 gives me 0. Does that make sense? Well, when x is 0, I'm at the top of the circle. Tangent line would be perfectly horizontal. Yeah, that makes sense. Cool, what happens at 1? Alright, I put 1 in, I get 1 over, oh dear, I get 1 over 0. That's undefined. That seems problematic, and plus minus or minus plus undefined. That seems problematic until I consider, where is this on the circle? Oh, it's on the far right side, so my tangent line runs perfectly vertical, so it doesn't have a nicely defined gradient. Okay, fine. Cool, last one. Sub in root 2 onto 2. Cool, so we get minus plus root 2 on 2 over 1 minus 1, root 1 minus square gives me, what's that, 2 on 4 is a half. Cool, gives me, what's this, root half, root 2 over 2 minus plus. Cool, these are the same because that's just reorganised into that. So I get minus plus 1. Well, that's a little bit weird. I've got a minus plus 1 or plus minus 1, depending on which way you want to say it. Doesn't really matter, you're talking about the same two values. Cool, so when x is root 2 on 2, where's that on the unit circle? Well, root 2 on 2, pretty big giveaway. I'm at 45 degrees. Well, 45 degrees, that's going to have a gradient of 1. And then if I talk about the tangent point here, I've got a gradient of negative 1 because they're at 90 degrees, because circles. But I could simultaneously be talking about down here, because the same x value gives me 2 points on that circle. So I could be getting a negative 1 gradient or a positive 1 gradient, depending on which of the two I'm talking about. Hence why we got these double values. Okay, great. So now we know what the results from the following should be. So let's try some implicit differentiation. Now, implicit differentiation is largely the same as differentiation. You just have to be a little bit careful how you treat the y's. So we've still got x squared plus y squared equals 1. Cool. Same rules hold. We can do linearity for it, so we can derive each individual part so long as they're plus and minus together. Derivative of that, nice boring, 2x. Cool. We now want to derive y squared. Okay, if we derive y, we just get, well, y prime, right? Because we had y, we derived, we've got y prime now. Great. If I derive y squared, how do I do that? Well, I can think of this as, this is a function, and this function is squared. Okay, if I want to derive a squared function, well, that's just chain rule. So, derivative of the inside would be y prime, derivative of the outside 2, original inside, power drops by 1, so it's just y. Cool, brilliant. Derivative of 1, 0. So this is now being derived into here. Cool, so dx of this entire thing now becomes this. Brilliant. Okay, well I've got this, great. Well, this looks nothing like this guy, what's going on? Well, hang on, I've just said that this whole thing derives to become this expression. Right, well what I want is y prime. Well, I've got a y prime, so now I just need to shuffle things around to get it by itself. Alright, so I've got y prime, I'm going to need to move this across, and then I'm going to have to divide by that. Or 2's cancel, negative x on y. Well, that's a little bit weird. I've got an expression for y prime in terms of x and y. That's not normal. What's going on here? Well, what is y? Well, we had an expression for that before up here. So if we put that in, we get minus x, and then y becomes all of this stuff. 1 minus x squared. Cool, okay. Well, can I neaten this up a bit? Yeah, this minus plus, I'll move up to the top. So instead of plus minus, now I've got minus plus. X over this, bang, bang, beautiful, matches nice and fine. Now, this seems a little bit weird because I'm like, hang on, I used this in order to get to the end of this. I didn't have to though, I was only doing that so that I could show that, yeah, these definitely represent the same thing. What we can do instead can save us a lot of time. Okay, I want to get these values. Alright, so x equals 0, x equals 1, and x equals root 2 on 2. Okay, well from that, I can very quickly figure out y, because I can just chuck it into this. Cool, so y would have to be 1, y would have to be 0, y would have to be root 2 on 2. Great. Y prime. Well, I've got an expression for y prime using just x and y. So this is where we start to save a whole lot of time. We don't have to deal with all these square roots, and particularly roots under roots and just getting all that garbage. We can just sidestep it entirely. So 0 over 1. So I get negative 0 over 1 gives me 0. Done. Beautiful. Agree. 1, 0. So I get y prime equals negative 1 over 0. Well, that's undefined. Cool. Agree. Great. Y prime equals, where are we? Now, this thing I should have put plus minus on it. Great. So I've got x on top, root 2 on 2, over plus minus root 2 on 2. Pretty quickly, that's obvious to be plus and minus 1, or minus and plus 1, depending on which way you want to talk about it. Beautiful. In fact, that should have had a minus there, so all these become reversed. So, we end up with the exact same result. We ended up with the exact same result. Now, you might be going, well, hang on, why are you bothering with having plus minus on minus plus? It means the same thing, right? So, yes, that by itself does mean the same thing. The reason that I'm being careful about flipping them around, what that means is that when I have a positive y, I get a negative y prime, and when I have this negative y, I ended up with a positive y prime. Now, because this is ambiguous, we end up at two different spots. Y is ambiguous. Y could be, because this is ambiguous, I end up with two possible y values. So this ordering just tells me which one matches with which. So if I'm on the positive side, then my gradient's negative 1. And if we think about a unit circle, when y is positive, gradient negative 1, yep. And vice versa, going up that way, yeah, makes sense. Beautiful. Okay. Well, that's cool. That gives us a new little bit of tricks. This wasn't that much really quicker than that at all. Sure, it saves us a bit of square roots and stuff, but is this really worth your time? I give you something far more annoying. Cool, so we've got this. Alright. If I wanted to derive this, what would I have to do normally? Well, I'd have to get y by itself, and that is going to suck. We can try to do it, so we can have all these y's out here. Actually, no, we can't even do that directly. We'll rewrite it first. 4 minus 2x, cool. I want to shuffle all this around a bit. So now I've got y squared plus x plus 3, lots of y equals 4 minus 2x. Okay, well now I'd have to force completing the square onto it, so I'm going to get this plus x plus 3 on 2 squared, then have to do an extra part here that will include x's in it, and then that still equals this, and then I still have to minus that off, then take the square root, then minus the, oh, this is going to get really messy really fast. Perhaps there's a better way. Let's try implicit. And unsurprisingly, yeah, this is going to work out well, otherwise why would I be bothered telling you about it? Okay. Cool, everything's all nicely linearly connected, pluses and minuses. 2x, that derives to just 2. 3y. Okay, if I have a function, that's y. If I have 3 times that function, how does its derivative behave? Well, it's just a scalar, so I just get 3y prime. Beautiful. Cool. We did this before, but just to reiterate, y is a function squared, that's chain rule. Derivative of the inside, y prime, derivative of the outside, original inside. That's y to the power of 1 now. Cool. Plus this. Oh, is this just y minus 1 times x because I'm fiddling around with that or something? No, this is a product because this is a function. X is still a function, multiplying another function. Okay, so now I've got product rule going on. All right, u prime, so 1 multiplied by this. In fact, I'll switch colors here to say all of this. We'll do this bit by bit. Cool, so 1 multiplied by original plus y prime by x. Or I could do that the other way around, u by v prime. So what have I done? U prime by v, v prime by u. You could do it the other way around, makes no difference, it's fine. Cool, and then the last bit, which commonly people will stuff up because it's so common. Usually you go, oh, it's constant, I'll just put it down. No, remember you're deriving. So I've got a 0 there. Very common error to make. Almost always, they will give you these relations equaling a constant, which is good because then that means almost always this thing is going to end up equaling 0. Beautiful. So now I've got this hideous expression. Okay, what do I actually want? I want y prime. Okay, well, let's shuffle everything that's not y prime off to the other side. So I've still got this guy, still got this guy, and still got this guy. In fact, I'll write that around the other way this time. Cool, everything else moved across, so I've got -2 and -y. Okay, great. Now that I've got all these here, just factor it out. 3 plus 2y plus x equals garbage. Great, and now isolate. 3 plus 2y plus x. Beautiful. Okay, so now I've got an expression for the derivative of this curve, which allows me to find gradients. Okay, great. Well, I know x is 2, but in order to use this, I need to know what y is. Not a problem. We've already described what this relation is, so let's just sum it in. Okay, at x equals 2, the whole original thing, 2 by 2 plus 3 by y, plus y squared, plus x, what was x do? 2y equals 4. Beautiful. 4 and 4 cancel each other off nicely. Great, we've got y squared plus 5y equals 0. Factor out a bit. Y plus 5 equals 0. Therefore, y could equal 0 or -5. Okie dokie. Well, we've got multiple options to pick now, so y prime is, we've got 2 different options. We'll run the 2 and the 0 first. No particular reason, just the number that I did first. So I've got -2 minus 0, 3 plus 2, 0, plus 2, which gives us what? -2 over 5. Beautiful. So at the point 2, 0, the gradient is -2/5. Fine. What about when we're at the point 2, -5? Okay, 2 minus -5. 3 plus 2 lots of -5 plus 2 equals, gives me +3 over -5, gives me -3/5. That's a 5. Yuck. Try that again. And that was at the point 2, -5. Beautiful. That's about as complicated as you'll get for the most part. Obviously, you could potentially have signs and quotient rules and all, and square roots and all sorts of ugly things in here, but it's still the same basic rules. Whenever you are doing implicit differentiation, just always think of y as a function. If you really want, you could replace all these y's with f of x, but then it starts to get pretty chunky pretty fast. You've just got to look at y and go, right, y is a function of x, so if I derive it, y would go to y prime, but anything other than that, I'm probably going to have to play around with some sort of chain rule, product rule, quotient rule. Cool. That is 6I. 6H is just practice for you guys. It's just a summary of the previous chapters, so it's just a whole lot of mix. Definitely do that before you do this to make sure you're totally happy with the basic differentiation, and then when you get into implicit, you won't have to think twice about too many things other than what to do with just a y. Cool. Best of luck to you. Email if you get stuck. Cheerio.